Hello, this is Aaron from Chef. In this video, I'm going to show you the NVIDIA Physx integration with inside Atom 3. With NVIDIA Physx, you can simulate a rigid body. You can convert any Maya geometry in a rigid body object. So let's select some object and create some rigid body from the new Physx menu here. So when you create a rigid body, Atoms will create a couple of nodes. So for every selected object, it creates an Atoms rigid body object. They basically expose all the rigid body attributes that you can set, and then connect every rigid body object to the Atom solver. Then Physx here, you need to enable the Physx to simulate. So just enable. And here you have a couple of parameters like subsamples for each frame, the scene scale. In this case, I scaled a bit the scene, so you can use like scale of 10. Gravity vector, number of threads that you can use for the Physx simulation, and some other Physx attribute here. So let's go back to the rigid body attribute here. First thing, you need to set up the type and the mesh type. So the type, you have three options here: static, dynamic, kinematic. Static is for static object, like, I don't know, the ground that is not moving during simulation. Kinematic are for objects that are some input animation from Maya. So if you have object with keyframe animation, you need to start to kinematic. So in kinematic mode, Physx will create a rigid body object for these objects, but the animation is driven from Maya and not from the solver itself. And then dynamic is for dynamic objects that are fully simulated by the solver. The second one is the mesh type. Atoms support those mesh type. So support plane, spheres, box, capsule, convex mesh, triangular mesh. Triangular mesh is just for static and kinematic objects, so not wrong, and a high field. So in this case, let's set up, for example, here, this one is a plane. Let's switch to plane. This one I want a sphere. Sphere, box is fine, and for the torus, just switch to convex mesh. And let's create some dynamic object. This one, dynamic. This one has some keyframe. So let's switch to kinematic, and this one, dynamic. Let's press play. So you can see this one has some keyframe. If you need to modify the input transform of your object, you need to modify the transform from the rigid body here, because the solver connects the output of the computation directly to the transform of each object. In this case, also if there were some animation keyframes on this object, are basically connected directly here. So for example, here, if you want to move, I don't know, a little bit up, you can move like this. The simulation. If you want debug the actual mesh that Physx is using, there is this option. For example, it's the debug draw. If you turn on, you can see basically the yellow mesh that is a representation of the actual mesh that the software is using internally. Okay, so now let's have a look to the other parameters. So the first one is use mass. So if this one is off, then Physx using the density attribute to compute the actual mass of your object, using obviously the density and the volume of your object. If you want to specify a specific mass, just turn on the use mass. And for example, here let's set it on 10 kilograms for this object. Then you have the linear and angular velocity. This one is a velocity applied to the rigid body object. For example, let's put some velocity here, and let's put also some angular velocity. This one is a max value for angular velocity. You have the normal damping and friction restitution value, like any other rigid body simulation. So then we have the dynamic on collision. So the dynamic on collision is useful on kinematic objects like this one. So what it does basically, it just converts the kinematic object in a dynamic object if this object is colliding with something. So let's turn on. Obviously here is not doing anything because obviously there is no collision. But if I move the sphere little bit here, let's see if we can make colliding. As you can see, now the cube is converted to a dynamic object when there is a collision between the sphere and the cube. So let's have a look to some other option that you have. Let's move back the sphere. So from the atoms Physx menu, you can basically use Maya fields to drive and apply forces to the rigid body. So for example, let's put a radial. Something here. Let's put the magnitude to -10. Let's see. That seems something more. Here. As you can see, all the three objects are attracted by the field, because it's basically is creating some forces on the space, and the rigid body are affected by these forces. One option here, if you go here and let's go here on the collision force threshold. So this option is used to convert a kinematic object in a dynamic object based on the forces that are applied on this object. So for example, if I put this one to, let's put to 100, and let's remove the animation. So as you can see, it's immediately converted to a dynamic object. But if we increase the force threshold to something like this, as you can see, is not affected because this one is the threshold on the force magnitude. Sorry, on the impulse magnitude. So let's have a look to the other attributes. So this disable collision event is useful only for the ragdoll simulation that disable all these events. I'll explain later during the ragdoll setup, or you can use this attribute here. Let's have a look to the stack on collision. So the stack on collision basically create a fixed constraint between two rigid bodies that are colliding together. This one is useful, for example, if you are simulating arrows that are colliding some object. So for example, let's turn on the stack on collision, the sphere, let's play the simulation. As you can see now, there is a constraint here between the two objects. And here you can set up a brake force. This one for linear force and torque force. here. For example, if I set up something like this, that maybe is too low. It's fine. So as you can see here, the constraint is valid, and then there is another collision that will break the constraint. The last two parameters are the collision pool and aggregates. So the collision pool, basically, you can set up a pool on every rigid body with an ID here, and the rigid bodies that are in the same collision pool, so with the same ID, will not colliding together. So for example, in this simulation, let me turn off the stack on collision. So for example, I can turn off the collision between the sphere and the cube. Just basically, let's put all these two objects in the same collision pool, and now basically they just intersect without collisions. The last thing is an aggregate. The aggregate is a parameter to speed up the collision computation. Please have a look to the NVIDIA Physx documentation. It's basically useful for when you have a ragdoll, all the rigid body will be in the same aggregate. So just put an ID here, and Physx will speed up the computation of the collision. Last parameter here for the every different mesh type. So here you have the plane attribute, box, sphere, capsule, and so on. And the last two parameters here for the rest and contact, this one is specific for Physx. Have a look to the Physx documentation for more information about this one. Now let's have a look to the constraints. So let me disable these two guys here, don't need right now. Let me create another rigid body. Let's create a cube. Okay, let's turn in a rigid body. What's a dynamic? Okay. So now let's create the constraint. You need to select two rigid body to create a constraint. First is the parents, and then the children, and then go Physx, create constraint. So the first thing that you need to do is to basically rotate the constraint node here and point the x-axis along towards the child's rigid body. This is because the Physx use the x-axis as a main axis during the constraint solver. So if I press play, now basically this one is a fixed constraint, so the second object is moving with the same transformation basically of the first rigid body. So for example, if I turn on the dynamic on this guy here, you see basically just fix it. Let's have a look at the parameter of the constraints. So there are different type of constraints. This one is a fixed. The distance, they basically just try to maintain the distance between the second object and the center of your constraint. As you can see here, there is no collision between the constraints because by default the rigid body that share the same constraint are not solved during the collision between each them. If you want to enable collision, you turn on this option here and disable. The spherical. For spherical, basically, it just this object can move around a sphere that is centered to the constraint transformation. The revolute is like a door hinge, so basically it lets you rotate the rigid body only along one axis, that is the x-axis at the moment. So for example, if I put something like that, as you can see, it can only rotate along one the x-axis. Okay, and now let's have a look to the other type. Prismatic, so it means that this object can move only along the x-axis. And then the last one is the D6, so you have 6 degrees of freedom, basically to simulate like a human joint. And now basically everything unlocked. You have basically the option here, the D6. So here there are some other parameters. This one are really specific for physics, so please have a look to the physics documentation about the projection and also about all the other flags here that you can stop. The breakable flag basically just turn on the brake option on the constraint, and here you have the force and torque limit brake. This one is the limit for the distance and spherical and revolute. So this one will be angle or will be distance. It depends on the type. And the same thing, the spring. This one is enable a spring constraint on top the actual constraint type. And I'm sorry, here you have more parameter for different type of constraints. Well, let's have a look to the D6 constraint. So here you can choose if you want lock, limits, or free motion on the linear or the angular for the different axes. So for example, let's put a free there. So free means that you can rotate everywhere along the sphere. If you want to lock some axis, for example, just keep the z-axis. And now I'll just have a look to the limit. So just turn limits. You have the distance if you have the free or limit, if you have limits on the linear motion. So you have the twist. So the twist, this one is the limit around the rotation around the x-axis. So you need to enable just when you have the limit on the x-axis. You can have a preview of the angle here, about from -50, 45 to 45. And then you have the swing and pyramid limit. So the swing is used basically when you have the Z or Y axis that has a limit. This one creates symmetrical limits between the negative and positive angle. So for example, here, if I change the Z, it changes basically symmetrically here. This one for Z and this one is for the Y. If you want more precise control, and you need different angle for the two parts, for the two angle you need to use the pyramid. So with the pyramid you have the minimum and maximum angle that you can set up. Put something like that, for example. So you see now there are some limit around this constraint here. And last thing is about drive. So basically you can add a motor drive on these constraints. Here there are options for different axes. This one is for linear motor. This one for the swing, twist, And the slurp, basically use the slurp instead of these two, because the slurp will be around the 3 axes at the same time. You have different option. So we have the parameter for the spring, force limits, and if you want to apply acceleration or a force here. And then here the drive pose. So basically with the drive, the Physx try to basically move the second rigid body to maintain basically this drive position for this constraint. But please have a look to the NVIDIA Physx documentation for more information about this one. The last thing that I want to show you is how you can use an atom simulation event to modify your physics simulation. So let's go to the Atoms UI, go to the simulation events, and add a new simulation event. With the simulation event here, you have access to all the different events of the Atom solver. So here, let me import Atoms Maya. Here you can access the Physx solver. So for example, to get the Physx, Atoms Maya, get Physx, and get from the solver node. Physx register, and then what you need to do is to enable the atom simulation, because it's different from the Physx one. So just go on the solver, just enable, and here you go. From here you can access the all rigid bodies. For example, for ED in Physx is rigid body is ID. So you can see here you have all the ID, and then can, for example, get the rigid body, the ID, go, and then for example you can apply a force B, add impulse atom smart dot vector 3, something, I don't know, like that. Display. There you go. So it's really easy. It's really easy to customize your simulation with Python if you want. For example, adding new forces, changing the state of some rigid body, or create new rigid body on the fly, or remove rigid body on the fly. So it's really up to you.